say whether a person went to college or not, and whether they have an income that's greater than 50K when they turn 30 or not. This is another variable, right? So given this data set, let's say we observe some correlation between these two variables. Now, how do we explain this correlation? So one explanation is to say, going to college indeed causes a larger income when I turn 30. Okay? And this is a perfectly plausible explanation, but it's not the only explanation. Maybe there's a third variable, right? That's my parents' income. And that explains the correlation that I see. So perhaps the true causal graph is that my parents' income, if it's larger, right, if it's large, one, then I'm more likely to go to college. And if my parents are wealthy, then maybe I'm more likely to have a larger income when I turn 30, because maybe I'll just inherit the family business or something, right? So this is another perfectly plausible causal explanation of the phenomena that you observe in the data, which is the dependence between these two variables. The reality is probably somewhere in between these two extremes, right? So probably going to college has some causal effect on your income, but also it's likely that your parents' wealth is going to play a role in confounding these relations between going to college and income variables. So parents' income here would be a confounder, maybe observed, maybe unobserved, but it will affect the bias, the dependence that you observe. Is my voice okay? Is this fine? The sound okay? So how do you assess causality if this is the reality? You need to conduct a randomized experiment, okay? Only when you conduct a randomized experiment, you will be able to cut off the incoming edges to going to college variable. Okay, what that looks like is the following. You need to collect 100 people, right? And you need to force half of them, let's say 50 of them, to go to college, wait 5 years, maybe 10 years, and then collect data, right, on their income at 30. You force the other half to not go to college. I don't know how I'll do it, maybe you'll tie them somewhere, but force them not to go to college, right? So you have to intervene. And that intervention completely eliminates the effect of parents' income on whether they are likely to go to college or not. And that's how you assess, by comparing these two subpopulations after your experiment, you can say the difference I observe must be because of this directed edge that goes between going to college and my income at 30. Okay, so this is why in practical studies you typically need to resort to randomized controlled trials to assess the efficacy of a drug, because we just assume we cannot control for every confounder. Okay, so let's say you have observational data. Now, how do you go from observational data to assessing causal effects? So this is what causal inference is about. Without having to conduct those randomized experiments, can we really do it, right? And there is something called adjustment, and this is just a very brief introduction, so I'm not coding it very smoothly here. But let's say this is your graph, right? So, and this is a graph taken from this paper. You have sex, and you have education level, income, and dash is some policy that they introduced to stop hypertension, dietary approach to stop hypertension. And they wanted to assess the causal effect of, I believe, education on the dash. So whether they actually used dash, this policy, or not. Okay? And here we have a bunch of variables. So sex here is going to be a confounder between these two variables, and income is going to be a mediator. Okay? So if you have access to this kind of graph, then what we know is that you should be controlling for sex, but you should not be controlling for income. You should not be controlling for the mediator. And what that, so this is the classification, sex a confounder, income is a mediator. And what that looks like is the following. Let's just get rid of the variable names, replace it with x, z, and y. Under certain assumptions, okay? And this is a potential outcome lingo that I'm using here. Positivity, consistency, and ignorability in this case, or conditional ignorability. We can say that the difference between two interventions, if I force education to be one, right? If I force this person to go to college, whether they are more likely to take this dash policy, to adopt it or not, versus if I force them to not go to college, let's say. So this difference, average treatment effect, can be obtained by solving two regression problems. Okay? The first one is the inner expectation, which is, actually I'll just explain over this table. So you have this data set of x, y, and z. You look at the value, you look at the rows where x equals 0, and you look at the rows where x equals 1 separately. Right? So we're going to solve two different expectations. For the star part, you look at these first three rows, and you regress y on z here. Okay, so that gives you a function. And after that, you need to take the average of the values of y with respect to the unconditional distribution of z. Okay, so this is just, you can see two regression problems you are solving, or just averaging at the end. And you do it for z equals 1 as well. And then you take the difference of these averages and or expectations, and that's how you can get to causal effect given this graph. But notice here I'm not using n in any way. So structural knowledge is important for you to know which variables to condition in these regression problems and which variables to not condition. I'm calling this regression because it's typically how it's called, right, in practical papers. In general, it's going to be adjustment, vector adjustment. We are going to see more detail of that later. Okay, any questions so far? I might be going a little fast. Just don't have any caliber of the audience, so I'm not sure. Yes?
This might be a better summary question for later, but I'm just curious how statisticians would approach this. Causal inference versus statistics, you know, correlation not being the same as causation.
Okay, so I don't want to start a fight here. Right? The question is, statisticians, what would they think about this? We should ask a statistician. I don't know if we have anyone in the room. But with my limited interaction with some statisticians, it depends. I think some are more flexible in the way they think they can adapt different models, but some are very much like, you know, Fisher. You have to run an RCT, you have to conduct a trial, otherwise there is no way. So it depends on which statistician we are asking. So let me leave it there.
Is there a philosophical point or underlying assumption where statistics break or differs from causal inference?
Underlying assumptions differ, yes, for sure. So I think when I talk about these graphs, I'm already making a bunch of assumptions there, right? So that's something we need to acknowledge. When I say there's a structural equation, there's an SCM, I'm already making an assumption that, oh, there is this structural equations that are assignment operators, and if I intervene, here's how that affects these equations. This whole thing is itself an assumption. So if you look at potential outcomes framework, they don't want to make these assumptions, they want to make different kinds of assumptions. So then you get different kinds of quantities that you can actually end up estimating. Versus if you are okay making these assumptions, then there are a bunch of other quantities you can also get to. So it's all about what you are willing to accept as a valid assumption. Thank you for the question. Okay, good. Okay, so what is really causal inference here? What we know today, based on the current literature, is that it is possible, if you are willing to make these assumptions that I was just hinting at, it's possible to estimate interventional distribution from observational data, the data set that you have, and the causal structure, and the causal graph. Okay? And the way we do this is through something called do-calculus rules. Okay, so do-calculus rules proposed by Julia, they are sufficient to convert any identifiable interventional query into a function, a deterministic function of the observed distribution, if that's at all possible. Sometimes it will be impossible, but we have a way to know when it's possible, and if it is, then we know how to get there. And this is given by sound and complete identification algorithms developed by Spitzer and Per and Tian and Per back in the day. So there is that literature if you're interested. Okay. Some other background I want to give before moving on. If you have a causal graph like this, right, with the assumptions that we just mentioned, and one more assumption I didn't add in the slide is the exogenous noise that you get here. Quickly get back there. The exogenous noise EI that you see here, let's suppose they are jointly independent. Okay, you don't have to make that assumption, but if you make that assumption, your life will be easier. So let's for now make that assumption. If you make that assumption, then we can view a causal graph as a dependency model, or specifically, we can view it as a Bayesian network. Okay? So if you have this causal structure, then you can read off conditional independent statements from that just by looking at the graph, and that is quite valuable. Okay? So for example, here you can say x1 and x2 must be statistically independent variables from each other. You can also conclude that x1 and x5 must be independent given x4 and x3. And you can also guess that perhaps these two variables will be dependent, x1 and x2 will be dependent if I condition on x4. Now that's not guaranteed, but it is more likely than not. Okay? So I'm hinting at some things. If anybody is interested, I can unpack what that means. But these are the things you can read off from the graph in general. Okay, so yeah, so takeaways, causal tag is a Bayesian network for the induced distribution. How many of you have heard of D-separation? Just so I have an idea of the audience. Okay, great. So for a lot of you, this is a repetition. So I'll do this quickly. So D-separation is the way that you can read off independences and condition dependences from the graph structure, from the causal graph structure. If you have not heard of this, it's going to take a while to get used to it for you. It is not going to be enough, but let me introduce it regardless. So if you have this chain, let's say, right, and you look at two variables u and v, these are the endpoints of the chain, you look at the path that connects them. Right? So here we have only one path, and along the path there are variables x and z. Now here, x has a tail, and z also has at least one tail, okay, adjacent to it. So you have two tails for z, one tail at x. But for y, you have two arrowheads. Okay, so when you have two arrowheads, that means it's called a collider. And when you have a collider, that collider doesn't let you travel through it. Okay, so you are kind of stuck here. So since you are stuck, this path is not deconnecting. If the path is not deconnecting, if no path is deconnecting, you say the variables are de-separated. And hence, here they are going to be statistically independent from each other. Now, what you can do to open this path is to condition. So if you condition on y, this collider becomes open. So you can travel through it. So now u and v becomes deconnected. If they are connected, then changing one through conditioning changes the other one. So u and v become dependent if you condition on y. If you further condition on a non-collider, conditioning on a non-collider blocks the path. So here you are going to condition on z, that will block the path, so they become independent again. So as you can see, you can start with independence, make them dependent, and then make them independent again, and so on. So it gets very complicated compared to undirected graphical models. Right? Undirected graphical models, if they are separated, you are done. Condition on as many things as you want, they will never be connected.